Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. This is the final video in the series of the assumptions and the statistical properties for OLS, and after this we'll be diving into exercises. So let's pay attention one last time to what the consequences are for the assumptions and what they mean for us when we do econometrics. As a small recap, these are all the assumptions that we have seen. Under the first 5 assumptions, we said that the OLS was unbiased. Then we added assumption number 6 in order to have a formula for the variance of the beta hat, meaning statistical property 2. At the same time, we had statistical property 3, which gave us also an unbiased estimator for the sigma square, meaning the sigma square hat. And remember, OLS being unbiased, I'm talking about statistical property 1 in here. And then we finally added assumption number 7 because we needed a way to do predictions and inferences. And without knowing the distribution of the beta hat, information that unfortunately we couldn't take from assumptions 1 to 6, then there wasn't really much need for the OLS otherwise, right? If we can't do the predictions. So we had it assumption number 7, which gave us the distribution of the error terms. And although it was unlikely to be true because it was a strong assumption, we said that it doesn't matter because as the sample size gets big enough, then we can use the central limit theorem and say that, well, it's approximately normally distributed. Now, adding assumption number 7 is very important because now under assumptions 1 to 7, we can actually find the actual distribution of the beta hats, right? So the beta hat j under these assumptions is normally distributed with a mean of beta j and a variance of sigma squared divided here by the sum of x ij minus x bar j 1 minus rj squared. And I'm going to highlight here a little bit the fact that I am not using a hat in here because this is the true parameter. So basically, if my assumptions 1 to 7 are fulfilled, then I'm estimating something that it's going towards the true parameter of the population. And this is the variance that I am given. This formula might help you connect the dots when we talked about the trade-off between unbiasedness and efficiency with this exercise when I was always trying to have the means of these distributions always fall into the true parameter betas in here. Now the implications of us having a distribution for the beta hat are very important, especially when we talk about hypothesis testing, confidence intervals, so anything to do with inferences, because from here, then if we use the standardization formula, which for some of you who might have done statistics might come very easy to remember, but for others not, we'll remind you, when we standardize, we take away the mean, so we subtract the mean and divide by the standard deviation. So when we have beta hat j minus beta j, because remember now this is the mean, divided by the standard deviation of the beta hat j. Now, this statistic will be normally distributed with a mean 0 and a variance of 1. So remember, we are standardizing, which means from a normal distribution, we're now getting to a standard normal distribution, okay? Also, one thing that we have to highlight is that this will be the case if the sigma square is known. And this is also the foundation, basically, of z-tests. So for those of you asking, well, what if sigma square is actually unknown? Which is actually what happens most of the cases in the exercises that you will be facing. Well, if sigma square is unknown, we know that through statistical property 3, we have an expression for an estimator for sigma hat, the sigma hat square. So making use of that information, then the standardized statistic that we just produced, it's no longer going to be normally distributed, but it's going to be t-distributed, which is a distribution with a shape that is very, very, very similar to the standard normal distribution, but slightly different at the same time. And that is because we have to add to this distribution degrees of freedom that are lost basically because of this unknown information that we had. So you will see t-distribution with degrees of freedom n minus k minus 1, where n is the sample size, k is the number of betas that you have, or of variables in your regression, and minus 1 for the intercept. Okay? So you having the distribution of the beta hat is the reason why you can do the hypothesis testing that is so common in most of the exercises, or even the hypothesis testing by eye by looking at the regression tables that are given to you in Stata. Now, one thing that you might probably not know, though, is that this distribution, so having the actual expression for the distribution in here, is what we call statistical property 5. Okay? The equivalent, the one in here where we had the standardized statistic, is also statistical property 5. And keep in mind, standard deviation in here is coming from the square root of the variance of the beta hat j, which, remember, beta hat, the variance of the beta hat j we had from statistical property 2. Since we couldn't apply this formula yet in the cases where the sigma is unknown, when we move to this other statistic that has the t-distribution, this is where we're actually jumping to statistical property 6, which means under assumptions 1 to 7, and given that we have the sigma square hat, then the test statistic is t-distributed with degrees of freedom and minus k minus 1. Okay? Hope this was all helpful to put all the pieces together. We went through quite a few of the assumptions, and it turned out that from the initial 4 statistical properties that we had mentioned, we have 2 additional ones that help us with the inferences. Thank you for following, and I'll see you in the next video.